All right, so we talked about a bar magnet, and I think another way to realize this and understand it, because I know when I was taught this, it was very difficult to understand it because they could never give me an analogy that would make sense. But if I said this was your car battery, and I know a car battery's got a post over here, and if you look underneath your hood, you'll notice there's a battery, believe it or not, that's 12 volts, unless that's probably a Tesla or a car built to the charge on one side, a positive cable, and a negative cable. If you look under your hood, you'll see this one's going to be probably red, and that's going to be black. And therefore, it's encased inside of a plastic case, and so there's an inside of the battery and there's an outside of the battery. And therefore, in reality, if you were to notice there's acid really in the battery, so don't start opening up your battery. It's a very strong acid. But we'll say that the battery had all negative charges on the inside and positive charges on the outside. There's a difference between the inside and the outside, and that's where you come up with the answer. It produces 12 volts. So when a battery discharges, what happens is it has to depolarize. So if this is polarized up here, then I would take that battery and to depolarize it, I'll just draw that same box again. And I'm going to write here depolarized. And I'm going to have that inside of the battery, same thing. I'm going to have those two terminals, one on each side, a positive here and a negative here. This is going to be the inside and this is going to be the outside. And now when I depolarize, I'm going to have some of those positive charges moving in and some of the negative charges moving out. And therefore that's depolarized. And therefore what the heart does, or any muscle cell or any nerve cell, it's going to have to repolarize. So when I go back to where I started, that's going to be called repolarize. So just remember, it's all to do with ions. So that's why I always say a good way to think about this is you went out on a really, really hot day and decided to cut 6 yards of grass, and you didn't drink much fluid. So when you went out and started cutting the grass, you started sweating. And you thought, wow, someone comes and says, here's a gallon of water. Drink this gallon of water right away. First of all, before you drank the water, you were kind of lightheaded. You were lightheaded because you were sweating and you were losing your electrolytes, your sodium, your potassium, your chloride. Someone comes out and they think, well, I'm going to really help this guy out. They're going to give you a gallon, we'll say, of ice cold water. So now you took a gallon of ice cold water and drank it. What did they do for you? They actually made you worse. Why was that? Well, if I give you more fluid, number one, I'm going to sweat more, but I'm also going to dilute the electrolytes that are left. So when I lost the electrolytes, out of my body, and I added all this fluid to it, it's called hemodilution. And therefore, if you took a blood draw on me with my electrolytes, you'd notice that now my electrolytes have even dropped even further down. The one I really got to watch is potassium, because potassium will stop your heart and put you into an arrhythmia very easily. So now that we look at that, we have this concept down. The last thing we just want to look at before we look at one more muscle is the concept of the EKG, which I stands for, remember, electrocardiogram. Started out by a guy named Einthoven. So if you ever see the word Einthoven, there's something called Einthoven's triangle. And so if you're losing like a 3-lead EKG, you'd see that you'd have a wire, you'd have a tab here, one here, and the three would come together. That's called Einthoven's triangle. So that's really the basis of an EKG, and to this day they still use that name. But if we look at an EKG, which we'll go into more detail in the second semester of this course, we're going to see something that kind of looks like this. I call this kind of a textbook EKG. But as I look at that, I'm just going to label it P, Q, R, S, and T. I see that this is a straight line here, followed by elevation, followed by a straight line, the depression, elevation, straight line, elevation, straight line. So therefore this straight line here we're looking at, and that's, we want to label that. So this we want to label P, the QRS, the T, and we want to say that that straight line there is going to be called the isoelectric point. And the isoelectric point is actually called the flat line. So if you stayed flatline for about 3 or 4 minutes, you wouldn't have to come back to class again because you would be dead. So kind of think you start out with an EKG with a flat line. You then have P, and P naturally, because we're looking at a 4-chambered heart. And remember that 4-chambered heart is going to have 2 atrium and 2 ventricle. It's going to have an RA, right atrium, RV, right ventricle, LA, left atrium, LV, left ventricle. Think of these are collecting chambers up here, so these are going to have the least amount of muscle mass. These are going to have the most amount of muscle mass here, so this is going to be kind of like this, and this is going to be real tiny like that. So just to get the big picture here as far as thickness of the myocardium, it's going to be the left ventricle is thicker than the right ventricle, is thicker than the left atrium, is thicker than the right atrium. So when I'm talking about this EKG, the P wave is going to stand for atrial, so that's your upper chambers, depolarization. In other words, the electrolytes have swapped sides, and therefore that's my upper chambers depolarizing. Then I'm going to have a little bit of a flat line. I'm then going to have what's called the QRS complex, and that's going to stand for ventricular depolarization. And then finally the T wave, you'll see a flat line T wave, and that's going to be ventricular repolarization. But if you notice, the one thing that's missing right now is that I don't see anywhere where I've labeled where the atria repolarize. Why don't I see that? Why didn't I label it? Well, I didn't, because remember I said that an EKG, think of it, is a measure of the gross electrical activity of the heart. So for example, if I said to you I did an EKG of you and your EKG was flat, and it was asystole, that doesn't mean that all of the heart cells are dead. It doesn't mean that they're all not firing. It just means in a gross appearance that most of the heart cells are not firing in any kind of a coordinated way. And therefore, unless I get that heart into some type of NSR or normal sinus rhythm, you're going to have to pronounce me DOA. Same thing with an EEG, an electroencephalogram. If I said someone had an opioid overdose and I hooked them up to an electroencephalogram and I said it was flatline, Does that mean that all of the brain cells are dead? And the answer is no. Because remember, it's just a measurement of the gross electrical activity of the brain. So we have to be very careful. There have been so many papers written how to determine brain death. Same thing with the heart. It used to be that we would do CPR for maybe 15 or 20 minutes, and now some studies show you can extend it as far as about 70 to 90 minutes, and people have come back and lived a normal life. So you have to be very, very careful in judgment calls or hurrying something up in healthcare. So therefore, that that atrial repolarization is somewhere right in here. So right where I'm drawing this arrow, that's going to be where I'm going to have my atrial repolarization. And therefore, it's going to be hidden in the QRS complex. So the QRS complex is going to have ventricular depolarization plus a hidden atrial repolarization. And then the last thing before we leave this EKG here is just remember that I talked a few minutes ago, but right here, from that line to that line, between those two is something called a cardiac cycle. And a cardiac cycle, I'm just going to go to a fresh page here, because it's a very important concept to not rush. So if I draw again what I'm calling that textbook EKG, PQRST, and I say there's a line from here and a line from here, and I said that's going to be a cardiac cycle. Remember, cardiac cycle is from the beginning of P to the end of T. And so if my heart was beating at 72 BPM, so if I have an HR heart rate of 72 BPM, I put 72 into 60, and it gives me every 8/10 of a second that I'd see that EKG waveform up above. If I went down and said my heart rate was 60 beats a minute, so if my HR was 60 BPM, I put 60 into 60, and that's every 1 second. But if I was to double that 72 and go up to a heart rate of 144, I would take 144 into 60. Remember, there's 60 seconds in a minute, and that's going to be 4/10 of a second. If I doubled that again, my heart rate, which happens all the time with people at 288, again, I would take 288 and divide that into 60, and that's every 2/10 of a second. Problem is, I can speed my heart rate up and up and up to probably up to 350 beats a minute, but it's totally ineffective because there's no blood in the chamber to actually pump out. So you have to be really careful that we think that, I'm on a treadmill and heart rate, we'll say, is 120 beats a minute, and I'm not really running that fast. But the guy next to me is very athletic, and he's running almost twice as fast as I am, but my heart rate's 120 and his heart rate is only 70. And the question is, what's wrong? What's wrong is he's developed what's called an athletic heart. He's actually pumping out more blood per beat than I am. He's got a better ejection fraction. The more blood I pump out per beat is the lower the heart rate I need to sustain the cells in my body. So that's a really significant piece. The last thing I just want to talk about is this concept of this bilateral, contralateral, ipsilateral. And so I just want to talk about one more muscle for today, and that's something called the SCM. So when you start reading your textbook and read about the muscle called the sternocleidomastoid, the sternocleidomastoid muscle. And of course, since we've already covered bones, we know that the word sterno means sternum. So therefore, this is the sternum. Cleido is the Latin word for clavicle. Mastoid is going to be the mastoid process of the temporal bone. So therefore, just think for a minute here. Sternum is going to be my breastbone. So therefore, that's going to be my axial skeleton. Clavicle is my collarbone. So that's going to be my appendicular skeleton. Mastoid process of the temporal bone on the side of my head is axial. And so when we start talking about this muscle here, we have to realize that this muscle, sternocleidomastoid, is going to have an O1. The first origin is the sternum. It's going to have a second origin, O2, which is the clavicle. And it's going to have the I, or insertion, which is the MP, mastoid process of the temporal bone, just as I have on the page before. So it's got, again, one of the origins is coming from the axial skeleton sternum. One of the origins is coming from the appendicular skeleton, the clavicle, and it's inserting on the axial skeleton, which is my cranium, on the mastoid process of my temporal bone. So now we know the name of the muscle, and we know where it starts and where it ends, and its origin insertion, just by knowing its name. Remember I said we also want to know what's the N. So let's do N next. The N, or nerve supply, is going to be CN11, and that's called the spinal accessory nerve. But I've also got to have an A. Remember, A stood for action. This is where it's a little tricky. It's a little tricky because if you kind of think, if I was to draw this muscle, and you'll see this same exact drawing in the book, you'll see how if I was to try to picture this muscle, here's going to be my sternum. And here's my clavicle coming off on either side. And here's my ear. So therefore, this is going to be the mastoid process of the temporal bone. And so therefore, I know that I already said that it's got an origin from the sternum. So O1 is here. So here's an origin. That's O1. It's going to come and cut across the clavicle. So that's O2. But then it's going to insert here. That's the I. And remember, that's going to be the mastoid process of the temporal bone. Remember, I'm going to have it on both sides. I'm going to have this one here, another origin. Going to cut across the clavicle. It's going to insert on the mastoid process of the temporal bone. And so I always use this muscle because it gives you a couple different terminologies that are really important in anatomy. There's unilateral, there's bilateral, there's ipsilateral, and there's contralateral. So let's look at this muscle. If I was to contract the right sternocleidomastoid muscle, so remember, kind of think when you're looking at this person here, this is his right side, and this is his left side. When you're looking down at him or looking at him, if I was to contract the right sternocleidomastoid muscle. So I'd be pulling down. Remember, origin is fixed, origin is fixed, insertion is movable. I'm going to be moving the head. So a unilateral contraction of the SCM or sternocleidomastoid yields or causes a contralateral rotation, which means it's going to rotate it to the opposite side. My right sternocleidomastoid turns my head to the left, and my left sternocleidomastoid turns my head to the right. The other thing you have to realize is that both of these muscles can contract at the same time. So that would be what's called a bilateral contraction. Bi is two. A bilateral contraction of the sternocleidomastoid. What's it going to do? Well, if you just look at this picture, if I pull down with this pen at this here on this side, and I pull down on this side at the same time, what's it going to do? It's going to pull my head down. So therefore, a bilateral contraction of sternocleidomastoid muscle is going to cause a head or neck flexion. And that's why this muscle got its name called the prayer muscle. It actually bows your head in prayer. So again, just think as I'm turning my head, when I'm turning my head like this, remember when we talked about bones, I said I've got the joint coming off of the dens, and remember that dens was the atlantoaxial joint. So when I turn my head from side to side, that's that atlantoaxial joint allowing for rotation. When I turn my head to the right, my left sternocleidomastoid is pulling my head to the right. When I take my right sternocleidomastoid muscle, it pulls my head to the left. When I take both of my sternocleidomastoid muscles, the right and the left, it's going to cause my head to flex, head or neck flexion. That's a bilateral contraction. Well, that's really kind of an overview and a summary of some muscles in that, and the next lectures we'll go into a little bit more detail on some and probably have a worksheet. And thank you.